Hello, Peter, can you hear me? So, welcome to week 15, lecture A. We have two more lectures left, so I'm going to leave the last lecture empty so you have more time to do your uh, project. Okay, let's, oh, this is not the one we want. So, this is really, yeah. So, did I share my screen? Probably not yet. So, okay, now you can see. So this is today's quiz. I'm hoping that you can take a look. Oh, do you guys, can you hear me, by the way? Okay, great. Daniel, thanks. Thanks, Greg. So today's quiz regarding brushed DC motors. What are the four basic possible types? That will get at very end of the lecture. I'm going to tell you. Also, at very end of the lecture, I'm going to tell you for a motor system, what does this mean? Okay. So basically, you have a motor, you have a shaft, then you have a load. So then basically, you have a motor, you have a load shaft, you have also damping because you are rotating. So you have a resistive torque. Okay. So we're going to explain this figure. It's called equivalent circuit for a DC motor system. But this is our first lecture on actuators. Again, I hope you know that there are just so many different types of motors. I hope some of you will pick up some of the motors so we can learn more from you. Um, but for this course time, I'm going to focus more on mechatronics related actuators. Okay, so we are going to see what are those actuators. Um, if you have a switch, that also considered as an on-off kind of actuator. Is that right? Yeah. So it's not sensor. Okay. Anyway, so what we are going to do is to go quickly through this deck of slides. Together we have quite a number of um, video clips, so you get appreciation of the actuators. I just made up the embedded all the videos into the slides. So I uploaded in our directory. You can check it out. So let me hide this thing out. So you can come into the files. You go to notes. Then you go to 15. So you are going to see that today we are now doing this mobile robot sensors. Okay, let's move on. So mechatronic systems sensor interface to the mechanic system and provide information to the system. Okay, so we already talked about sensors already. Okay, so we are going to focus more on the actuators. But before that, we are going to go quickly. For mechatronics, usually you need to measure the motion, so angular and linear position, speed, acceleration, force, and torque, and something called a dot. It's called jerk. Okay, and so on and so forth. The sensor, usually you need to detect whether there's an obstacle when you have a mobile robot moving around. You don't want to hit something. So that's also a distance measure, how close. Okay. and people recognition as well. Okay, so for those sensors for typical robots, I ask you to count 5 types: potentiometers, optic detectors. We already covered all these: speedometer or tachometer, accelerometer, piezoelectric sensors for force and torque. And of course, you heard about GPS, about external referential, laser gyroscope, things like sonar. You have a limit switch. So if you hit, then you will generate a signal. You know you hit. Or you have a proximity sensor. Remember last time we talked about this proximity sensor. Okay. And sometimes you use a very simple infrared emitter detector. Okay. So remember you have in the PITR you have a PIR sensor to detect the motion. It's called a motion detector. So if you somebody close, then the light will be on. I have such thing in the backyard. So of course, a camera is also a sensor, can do multiple things, and also voice. Okay, so if you today you have this thing called Alexia, Alexia, or Amazon. What is Amazon? Amazon Dot or something. Anyway, so this is angular position. You can use the gear before the gear, sensor placed after the gear. So there is a different configurations. Okay. So those are usually measured by a potentiometer. Okay. But that potentiometer usually is not for the full rotation. But if you have full rotation, you usually use optical shaft encoder. Okay. So this is a typical potentiometer. Okay. Then we talked about potentiometer for linear versus rotational. And we have seen something called arrows, like this called load effect. So we have seen this before, okay? So then this is an encoder. So you have an index. So this is like an index. It generates 1 pulse per revolution, okay? Others just the windows, okay? Then you have a light source, you have a receiver, okay? So basically, this is a side look, okay? So you have a light source, you have a receiver, and whenever you have a window going, then you have pauses, okay? We have seen that. Photo detectors, yeah, we have seen this already, okay? We have light difference, then you have a V out is difference, or something like this, generate pauses. Okay, so we have seen this thing before. We have 2 channels. You have 2 sources and 2 pickups. So then you have a quadrature. So then you have 4 times more resolution. Okay. And also people using this as optic detector for linear motions. They also have a 2 light source and 2 receiver. Okay. So it's called an optical ruler. Okay. Okay. So this is called absolute angular position. So you can see there are so many bits in here. Okay. Okay. So then you have an array of this light source, then your array of this type of receiver, then you have parallel multiple channels. Then all the positions as absolute. Okay. Okay. So there are 2 types of coding. One is called gray code. Okay. Another one is a binary code. Okay. So which one is better? Gray code is better because every time there's only 1 bit change. Well, so binary code, gray code, we talk about that. Resolution and switches. Okay. So these switches, you have usually this is called e-stop. E-stop. Okay. So it's called emergency stop. So you push the red button, everything should stop. All right, there are many types of. So I think you should know something here. When you have there's a button, right? So this button, you press down, then it will connect. So then this is called normally open, okay? Okay. But this one, if we push, then it will disconnect. So this is normally closed. Okay? Normally closed, normally open. So there's two different notation. And there's also something like SPDT, double throw. So single pole, single pole, single through. So this is usually we use, okay? That's one for one thing. But there are also something called double throw and single pole. So this is a single pole, you have double through, okay? SPST, SPDT, okay? So these acronyms, you should say, oh, you should not say, oh, Dr. Chen, you never taught me. Yeah, you should know, okay? And tactile sensor is actually a topic of research today, okay? So think about your muscle and your skin, okay? You can sense. People are developing something on that as well, as a tactile sensor. This is very useful for grasping the robotic hand, grasping your fingertip. Basically, hopefully, your fingertip can sense how hard you are grasping, right? So the tactile sensor basically is based on an array of those conductor and sectors and electrodes. So if you want to know more, I hope some of you will choose tactile sensor and get into the literature to see what's in the market, what's the working principle. But I think here I just mentioned this is possible today. Yeah, I think a pyroelectric sensor. So generates surface electric charge exposed to heat. If you too much heat, the heat will convert to that. So this is to form a kind of infrared radiation. Get know what's the temperature. Okay. But there's a field of view though. There's a field of view. So there's a field of view. Field of view. Okay. Field of view. It's usually narrow, like 10 degrees. 10 degrees is very narrow, okay? Very narrow. Okay. And this is a pyroelectrical sensor. And so there's a field of view, okay? So there's a heat source movement. You cross this one, it will generate a signal. So it could be used for motion detection for human, okay? So pyroelectric sensors, okay? PIR, you have a dedicated sensor you can buy. Okay? Some of them with some larger view angles. And sonar, you heard about this because of the return. It's called sonar. Is called sound, navigate, and ranging. Ranging, check the distance, how far away the fish is from here. So usually it's to track the enemy submarines in World War II. Sonar was developed there. But today, sonar is also cheap sensors for even driverless car navigation. It's widely used in the robot. There's dedicated module that again it has a field of view, okay, and effective distance. If something is far away, this cannot distinguish. Okay, there's an effective range of the sensor. So sonar. So I just quickly go through some of the stuff for you. Let me see if the.
This is an example of a single-phase induction motor, typical of what you would find in a household application. This particular motor is from an attic ventilator fan. I'm going to remove the casing to show the pieces and parts of the motor,
Like in
the
your
stator
Coil.
and rotor, the type of construction that makes it uniquely an induction motor. As you can see, the rotor assembly rotates around the stator coils. The rotor in an induction motor is the classic squirrel cage design. The squirrel cage is embedded into the core, which makes it difficult to see the actual squirrel cage. Taking a closer look, looking at these lines going across, those are the individual bars of the squirrel cage. The lines are on a slant here, where the bars are angled in order to develop startup torque in this particular single-phase motor. The actual rotor bars are shorted out on both ends by shorting rings. The stator in this particular motor uses salient pole construction. Notice that the windings are wrapped on parts of the core that protrude toward the center or rotor, which is, of course, salient pole construction versus cylindrical construction. This particular motor obviously has 6 poles.
This is a brushless DC motor from a computer fan that helps keep the circuit boards inside of a computer from overheating. Like a permanent magnet DC motor, it has permanent magnets in the stator of the motor, and it has coils on the rotor. Unlike a permanent magnet DC motor that uses commutators to switch the direction of current in the rotor coils, this motor has a series of Hall effect sensors inside, these little white things beneath the circuit board.
Yeah, it could be more efficient. Yeah, but it will be more expensive.
Inside of a computer from. This is a brushless DC motor.
Let me see if I missed any.
This is a.
Then this one.
What we're looking at here is a typical hard disk drive found in your computer. These are the disk, and the motor, the spindle motor, is basically a 3-phase AC motor, also known as a brushless DC motor. Here's the magnetic recording head. It's held on an arm, which is essentially a radial actuator, which is activated by a voice coil motor hidden in here beneath this magnet stack. When the power is applied to it, first thing it does is it will spin up. Once it gets to full speed, it reads sector marks off of the disk. The head then goes out, reads information from various different tracks, and it calibrates the voice coil motor for the radial actuation. The whole thing is run by a microcontroller. It's a Motorola microprocessor right here. And in this case, it's got some ROM chips on it with code stored for the microcontroller. Over here is a bank of FETs, which are for running the voice coil motor and the spindle motor. It's got some high-speed video A to D for interpretation of the head signal to digitize it, and an AT interface chip, which sends signals back and forth to the computer. What we're looking at here.
So you know that I worked in the hard disk drive industry. I know this one very well. I'm still running my patent algorithms. It's fantastic Mechatronics application. So we take it for granted. The plugin work for years without any problem. Take it for granted. But inside, we really need a synergistic method of Mechatronics design. And the volume is very high, so you need to be very low cost as possible.
This is a small permanent magnet DC motor that's rated at about 1.5 to 3 volts. It consists of an outer stator, shown here, with the rotor inside of it. And you can see the permanent magnets on the inside of the stator housing. This is a clearer view of the magnets. The magnets provide fields, radial field lines, that interact with the coils of the rotor. This is what the field lines look like. The inside surface of the magnets are at a south pole, the outer surface is at a north pole, creating these field lines that are radially oriented towards the armature of the motor. There are actually 2 different types of magnets in the motor, and as you can see, because they attract each other in this orientation, one face must be north, the other face must be south. And likewise, if we try to press them together this way, they repel each other. They do not want to stick together.
Yeah.
This is the rotor and the brush support, which is also the end cap of the motor. The brushes are small copper tabs that keep contact with the commutator as the rotor rotates. The commutator has 1, 2, 3 separated segments on it that make contact with these two brushes as it turns. The result of that is that the coils, there are 3 separate coils in the motor, receive current in different directions, creating magnetic fields that are intensified by these laminated poles here that interact with the fixed fields of the stator, causing the motor to rotate. This is an electromagnetically coupled brushless DC motor gear pump. It consists of drive electronics that take input from a manual potentiometer or an external voltage or current signal, and it controls the speed of the pump based on those signals. This unit generates rotating magnetic fields in fixed stator coils. The stator fields magnetically couple to a rotor which is attached to the gear pump. The rotor is sealed from the stator. The only connection is the magnetic coupling. The pump has an inlet and an outlet. These are the coils inside the stator, and again the electronics in the control unit have the magnetic field rotate around the stator, and these stator fields interact with the rotor, which is inside the sealed unit here. This is a close-up of the gear pump. The rotor turns this center gear, which messes with this outer gear, and these turn within a housing that allow fluid to flow from the inlet to the outlet. These are helical spur gears. Here's a close-up of the gear pump in its housing. As the rotor turns the center gear in one direction, fluid from the inlet is trapped between the gear teeth, which travel around the housing and can exit at the outlet. And this happens on both gears. Again, fluid comes in the inlet, travels between the gear teeth, around the housing, out to the outlet.
So it's cool, right?
This is an electromagnetic.
So let's continue. Maybe this is.
There are 2 primarily different types of DC motors that we use in our mechatronic designs: stepper motors and permanent magnet DC motors. The stepper motor is also a permanent magnet DC motor, but it has the interesting capability of that it will move in a digital or incremental rotation rather than continuous motion that we obtain from the DC motors. Starting with the DC motors, we show 3 different types of DC motors. This is a very small hobby DC motor, 3-volt motor, a slightly larger DC motor, and this is an even larger DC motor, and you'll notice that there's a gearbox that's an integral part of the DC motor. Note that with a DC motor you always have 2 wires for power and ground. And the DC motor then is a motor that is speed controlled by the value of the voltage applied to the DC motor. The stepper motor, on the other hand, there are different types. You'll notice that this stepper motor has 4 leads. This stepper motor has 6 leads. This is a bipolar stepper motor. This is a unipolar stepper motor. And the drive circuits that are required for these stepper motors are more complex than the DC motors and will depend upon whether it's a bipolar or a unipolar DC motor. There are 2.
Okay, let's see a motion control system.
This is a typical commercial servo motor system. It consists of DC motors with digital encoders that provide position feedback. This is the amplifier that comes with the servo system that takes small voltage signals from the controller and provides large enough currents to generate significant torques in the motor. This is the controller box that has electronics in it that allow interface to a personal computer. So you can control the servo system from a personal computer with software via a serial port or a USB port. And there are connectors that allow cables to be connected to one of these breakout panels that allow you to have access to all of the pertinent signals involved with the system. The encoders provide position feedback so that the controller can perform closed-loop PID control to accurately control position of the motor.
So this is actually a typical XY stage. So basically you have two motors, one moving X, one moving Y. So by doing that, you can locate which position it is. So you can see 3D printer, there's XY, stage. So it's the same idea. But it needs to be controlled to arbitrary point with high accuracy. So you need feedback control, which usually is used a PID control.
This is a typical commercial.
So let's see one more. This is a servo motor. Okay.
This is a stepper motor position and speed controller. We have a PIC 16F84 controlling everything. We have 4 normally open push button switches.
Normally open.
We have another switch that puts us in and out of speed control mode. The speed of the motor is controlled by a potentiometer. We have an external A to D converter. It's a national semiconductor, ADC0A31. It reads the voltage from the potentiometer and sends digital data to the PIC. We have 2 LEDs, one to indicate that power is applied, another one to indicate whether or not we're in speed control mode. We're using eLab's EDE 1200 unipolar stepper driver and a chip with Darlington transistors. That's a ULN 2003A. And those send pulses to the stepper motor in the proper sequence. Okay. The 4 position buttons position the motor at the current position, that's the first one, at the 45-degree position, the second one, at the 90-degree position, the third button, and at the 180-degree position, the fourth button. So there we move from the 45-degree position and back to the 0-degree position. That's the fourth button, which moves to the 180-degree position. And you can see the motor taking one step at a time. This particular motor has 7.5 degrees per step. Okay, now to enter speed control mode, we press the other button. The red LED appears, indicating that we're in speed control mode. Now the potentiometer is active. If you turn it to the right a small amount, it's turning the motor clockwise. And as we turn it further, it increases the speed of the motor by decreasing the pause between each step. We can also turn the potentiometer counterclockwise and have the motor turn in the other direction. Again, the speed is proportional to the potentiometer displacement. Now we're back in position mode. The speed LED is off, but the speed we're running at, which is very fast, is used to move to the index positions. It's important to note that that was a very fast speed, and if you try to move to the positions starting at 0 speed and immediately go to that fast speed, it cannot track properly, and the motor does not move the full 45 degrees, or in this case the full 180. So you just buzz in that one place because the motor is stepping too fast for the rotor to respond. If we go back into speed mode and move to a slower speed, and again enter position mode, now the motor can track the positions starting from 0 speed. Again, to move a stepper motor at a fast speed, you have to gradually accelerate to get to that speed. You can't start at that speed immediately.
Okay, so if we are not in the COVID time, we would be able to go to the lab and do some hands-on labs like this. But unfortunately, we can only watch the movie today. But this is still better. You have some ideas about the actuators and the motors. On the other hand, I told you multiple times that what's going on? I want to get out. Okay, now I get out. Okay. We need to learn some of those foundations. Okay, foundations. So let's see. I have some other things I want to show you quickly. Then we dive into the foundation part. Okay. So we just visually know something here regarding DC motors. So basic principle is if you have an S in here, so then this is a rotation. So actually, this is not stable because S will push S away. So it will keep going. Then you're attracted to this, then keep going. We reverse that polarity, then we'll start to turn. So let me, so you have seen this before. So this is a stepper motor. By adding the coils at a different, so this is 1, 2, 3. So there are 3 pairs of coils. If they are applied alternatively, repeatedly, they are this is going to start to move. It's called the basic principle of stepping motor. Okay. So by adding the winding with different sequence, okay. Let me do this. So for brushed type, today we are going to learn brushed type. Next lecture, we are going to look into a brushless type, okay? For brushed type is DC motors. So you power supply with DC, and then you have a commutator, okay, in here. Then these are considered as a brush, goes with this, okay? So then you will change polarity, okay? So look at this one, you will see that the brush is not changing, okay? The commutator is changing, okay? So this is the battery, we provide this. So you can see you have south and north in between. This is how the DC motor operates, okay? Operates because of the change of A and S, A and S, where you have this brush, okay? So elementary theory for DC permanent magnet motors, I'm going to go through with you this one in the next deck of slides. But so this is a motor, you have an excitation circuit, okay? So we should understand in a way called equivalent circuit. This is not in the equivalent circuit. So we'll keep going this one. This is called external speed, torque, okay? Speed is inversely proportional to the torque, okay? So this is the omega. Speed, when speed is high, the torque is slow. When torque is high, then speed is low. So that's the external characteristic. So there is also store current, okay, store current when the torque is too high, okay. You have to, because the torque is high, then basically I got stuck, I cannot move. So we're going to go through in the next deck of slides. We are also going to talk hydraulic and pneumatic next time, not today, but you know that in reality, you are going to meet hydraulic motors and pneumatic motors as well. You have seen this hydraulic or pneumatic. Hydraulic is by liquid, pneumatic is by compressed air. Okay. So the key word for using hydraulic or pneumatic method is called the power density, okay, power density. The power density means you have speed, you have torque, okay, you have torque. So for motors, okay, for motors, can only run at high speed, but the torque is relatively low, okay. But if you need to use a very high speed, very high torque, medium speed, then you should go to hydraulic. That's why hydraulic is a huge torque. So we have a dedicated hydraulic and pneumatic slides to introduce in a detailed way, but we don't have time to do that. regarding gears, I hope you, I think mechanical engineering students knows this pretty well. So probably we can skip that regarding gear ratio. Okay, different types of gears. Servo motor, we have seen that. We have seen the movie clip of servo motor. So basically, just give you what's the pulse duration. Okay, pulse duration. So this is also called duty cycle. Okay, duty cycle. So this is like from this is the this is the period, okay, and this is the 1. This is all 0. So there's a duty cycle. In this case, probably is like 5%. This one probably is higher versus this. So this divided by that. So duty. So it's a duty cycle. Duty cycle. It's called duty cycle. Okay, duty cycle. If we have a 50% duty cycle, then you should draw something like this. So this is 50, okay? 50%, half. Okay? So duty cycle. By tuning this duty cycle, then your the pulse code modulated signal, the servo interprets a defined desired position on the potentiometer. So it will change. It will move the angle. So the moving the angle is proportional to the duty cycle. There's another thing usually. So remember, we have a controller. We add this one to the plant, or motor start to have this feedback control. So we know that there are sensors here. We know that this block H is not 1, but we assume it's 1. So we know that this is actuator here. Okay, we just treat it as 1, but in reality, it's not 1. Okay, it's not 1. So please be careful. Although we didn't draw this, but you should know the existence of the actuator and the sensors here. They're all treated as 1 in the textbook. Okay, but in our case, we still need to have another thing called power amplifier. Power amplifier. Okay, so if the signal out from this control circuit, that signal is not strong enough in terms of power. Okay. Power is proportional to I times V, right? Okay. So yeah, if V is okay, then I is usually small. Okay, usually small. So how to make that the total power of the control signal? You need a power amplifier. Okay, power amplifier. So so that is something we call, sometimes we call this is a power amplification. It's also called H bridge. So this is, you have seen the switch. Then what about you have a motor, you have a supply voltage, and you have switch of those power. And so then if you do this, this is called H bridge. Okay, H bridge is if these two are off and these are on, so they go this way. Okay, and you can turn on from this way. Okay, so this is called H bridge. It's usually working in that principle. Okay, so yeah, so we can have a logic to control the off and on and off logic, so we can make this motor. So that's a digital logic. But today you don't have to worry. There is integrated circuit do the work. Okay, you give a signal, they know how fast it will turn off and on. There will not be something like arrow. It's all on, then it's a short circuit. No, it's not going to happen that way. Okay. Yeah, this is the short circuit. We don't want to do that. So this is called why we usually do this PWM, pulse width modulation. Okay, open closing in a different interval. Okay, that PWM is called a PC, pulse code for the servo motor. So the motor will the speed, okay, will be proportional to your PWM duty cycle. So for example, pulse width ratio, this is a duty cycle basically, on time versus period, okay? So this is duty cycle, okay? So that duty cycle is proportional to your level of this dashed line. If you use Fourier series expansion, so you have a constant term like average, DC component. Okay, so to do that, you may wonder what are those high order harmonics? So those could be filtered out or just produce noise versus heat. So it's not that efficient. Okay. So that depends on the period. If the period is small, so this frequency is high, so the efficiency is high. There are many different PWM and edge bridge circuits to do the same work. So this basic principle for doing this power amplification is like that. So I'm going to do the main part of today's lecture. You can see we have so many slides. We have about 100 slides, 103. So week 15, I'm hoping that you are able to understand direct current motors with all the basic knowledge. You have seen the movie, you have seen, I quickly go through some of the basics, but what is the real thing behind? So basically we should cover what is the elementary direct current machine. I have shown you that, I'll revisit that. Then this part is very hard and messy regarding how the windings are going inside. You can watch in the YouTube. Some people do this handmade windings of those stators. That's actually can be controlled with different characteristics. Especially in the drones, I saw people do hand windings of the motors. Okay. From our system point of view, it's better we understand what is torque equations. This is also called exterior or external characteristic of motors. There are 4 types of DC machines. So this is in the quiz part. So one is a separate winding excitation. Another one's shunt connected and series connected and compound connected. Okay. And so I'll show this one to you towards the end. Okay. Then, of course, we hope we have a transfer function derived for a DC motor system with a block diagram. Then, especially, we are going to meet the permanent magnet DC motors a lot. Then, what is that? Then, in the control, how we do this closed loop control. We talked about gear system. There is also an interesting literature talking about optimal gear ratio. It's like impedance matching stuff, okay? And some basic ideas of motor selection. You should consider what factors. So this is basically for a specific class of actuators. You should give basic working principle. What's the external characteristic? What is the transfer function? How to control it? And what are the selection considerations? Please add that, okay? So brushed, I already told you why we need a brushed, okay? Because we need to do the commutation. do the commutation. It was widely used in the past, but not today, because the brushless DC motors are so widely used today. It's cheaper and easier. For mechatronics engineer, we should consider shunt connected DC motors and permanent magnet DC motors. They have similar operating characteristics. So basically, a motor is to turn the mechanical energy into electrical energy, or electrical energy to mechanical energy. So these two can be interchanged. Okay. As last time we talked about tachometer to measure the speed. Okay, so tachometer measure. So it's basically if your motor is turning, and portion of the mechanical energy will turn into electrical energy, generate. So that's called tachometer. Is a generator, basically. Okay. So let's take a look of elementary DC machine. So it's called two-pole DC machine. Okay, so let's take a look two-pole elementary machine. Usually you have field winding for the stator. So you need to, so this is something like, you need to, what I'm doing. Okay, it's here. So basic idea is that you need to generate some sort of electromagnetic flux, okay, for you to cut through for conductor, okay, to cut through to be able to produce the electrical and mechanical energy conversion, okay. So then you need somebody to generate the mag flux, okay. That's called field winding. You generate a magnetic field, okay. So this is a magnetic field, okay. And then you also need a rotor. Rotor is called armature, okay. The armature is this guy, okay. This is armature. This is the field, stator. This is armature, okay. Using S and A, okay. Then commutator is a semicircle, usually it's copper segment mounted on the shaft at the end of the rotor. They can insulate from one another, so it's like a two half. In between, there's an insulation. So, okay. So each terminal of the motor coil is connected to the copper segment. So this is called a commutator. Then there is also what? Brush, okay? That's a brush. So there's a carbon brush, okay? The reason we use carbon, because the carbon will give you enough lubricant. So that right on top of the copper segment. So what you have seen the movie, right? So voltage equation for the field winding. So it's a simple one. You have a supply, voltage supply. You have this is a resistor. This is an inductor. Okay. So here we are using a flux, but remember this is LD lambda. Lambda is actually the field and armature kind of coupled inductance. Then you have field to field self-inductance. It's called self-inductance. Okay, let's go to this one. Go to this figure. Okay. So first of all, is stator. So the whole thing. If I put everything into the blue dash shaded area, so this is something there. It's not going to change. So it's fixed on the floor. Okay, everything is fixed on the floor. Everything is fixed. Okay. So here is the air gap. Okay, air gap. But through here you have a shaft. Okay. So then you keep the air gap. So this thing is called, the whole thing here, let me do another color. The whole thing here, this is the rotor, okay? This is the rotor, okay? In a rotor, so you have two semi-circle copper, this one. In between the copper, you have this black thing. This is called insulation, okay? So these two coppers are not connected together. But there is maybe this one, purple. So there is this guy, purple one, and the purple one is a carbon wiper, okay? Carbon wiper have a contact to the copper. So when you turn, okay, if you pass through the insulator, then the coil, so this is the coil. Coil is here. This is the coil. You have one coil, okay? The coil will start to turn, okay? Start to turn. So the coil here, you have a cross in here. You have crossing. This is another one is dot. So this is like you have a coil, okay? Okay. So you have a coil, but if you look into inside, so this is current moving inside, then the current coming outside is dot, okay? It's dot. So this is the coil, okay? This is the coil. So let me see. For the blue part, so the basic thing is to produce a magnetic field, okay? Magnetic field. So this is called field excitation circuit. So this is a field excitation. You provide the VF in there, okay? Then you will go through inductor, okay, and a resistor, okay? So so you have F1, F1 prime. So you have F1 going through the winding F1 prime. So there's a winding circling on that. Make sense? And same thing here, you have a winding here, F2 and F. So you can see F2, then F2 prime, okay? F2 prime is get out. F2 is cross is inside, okay? Perpendicular into the paper, into the screen. In and out, okay? So as if you look from here, this is in, this is out, okay? So then you can see the coils are connected in such a way, from F1 to F1 prime. Then you have F1 prime and F2 are connected, then F2 prime. So by doing this one, you have two coils, one coil here, another coil here. One is on this pole, okay, another one on this pole. So by doing that, you can generate the field winding, okay? Okay, so I think by doing that, we can say that we have a magnetic field, okay, magnetic field. So if I give the coil voltage, then the coil will start to turn, okay? So that becomes a motor to convert electrical energy to mechanical energy. On the other hand, if I have a shaft connected to this coil and make the coil move, then the coil will generate electricity, turning mechanical energy into electrical energy. So this is called a machine. This machine can be either motor or generator, okay? So these are the gap. I told you there's a gap in here, this gap, okay? So this is the gap, air gap. So this is this side is a field excitation is called on a stator, okay, stator. And here, this is the rotor side, okay, rotor side. So if you give VA, A is amateur, okay, A is amateur. You give the voltage, then you will have a current, okay. Then this is the motor. You have a shaft. This shaft can be connected to a load, okay. So then you can bring the load to turn, like your fan, like your many other motor applications. On the other hand, some of the motors attached with a tachometer, then you make it turn, then this VA will be generated, okay? Okay, so that's for commutation of elementary DC motors. So basically, now let's talk about giving a current, okay? Give a current. When this one turns, after the commutation, otherwise it will become something like this. Then they'll make this current, make this voltage in amateur produced is like this is called like rectified. Like this is also called half wave rectification to make those sinusoids into this format. Okay, so then according to the DC component is something like this big. You can do better by inserting a capacitor, okay, inserting a capacitor to make this like the real curve is like this, okay, like this. So that's but you may say, what if I don't want that? This is a two-pole basic principle like this. But what if I use multi with parallel armature windings? Okay, so I have multiple windings at a different position. So yes, it's still possible that you make the sinusoid in this because you are doing commutation. Okay, commutation. We'll have multiple coils. Then you generate multiple. So the final output signal is adding together because of the winding connection. So then it will become this. So this is more like a DC, okay? More like a DC. But this is a complication in terms of the construction, and it could be more expensive. So, but just for the basic knowledge, okay? So saying that we have a multiple parallel armature windings, they have like a counterclockwise separated, okay? So idealized that we can lump everything idealized. So this is called the basic equivalent circuit. So you have field excitation resistance in the circuit, the resistance, and you have field excitation circuit inductance. Okay. Then for the armature side, okay, rotor side, this is a stator. Okay, this is stator. This is a rotor. On the rotor side, you also have the same. Okay, so you have a shaft. Okay, you can generate that. So this one will give you back EMF. Okay, electromotive force, back EMF. So to balance everything, okay. I don't think you need to know all this complicated winding and commutation configurations. So it's very tough, okay, very tough. But we have seen in this end view, but we can also have a cross-sectional view, okay? So you can roughly know what's going on here. So you have stator winding, you have a rotor and a rotor winding, okay? Air gap is just it's illustrated, but it's actually very small, okay? It's aligned. We don't need to go through this on now. I want you to take a look of voltage torque equation. So basically we are here, it's called equivalent circuit, okay? Basically this is our field excitation circuit, and this is armature circuit. The armature itself has AA. AA is like a mutual inductance, okay, mutual inductance. This is also FF, it's a field. But there are also coupling. Think about coupling, AF, okay, AF. So that mutual inductance, LAF is a mutual inductance between the field and the rotating armature coils, okay. AF is self-inductance for the field windings. AA is like self-inductance for the armature windings, rotor speed. So we know that this back EMF is also a voltage, okay? We'll have an equivalent voltage induced in this motor, rotor, okay? So it's proportional to omega R, okay, omega R, like the speed. You have larger speed, you have a larger back EMF, okay? And this is also linked to the IF, okay? The field current, okay? Field current, IF. So the IF is controlled by VF, okay? So that's why if you change VF, you are going to change everything, change everything. So you can change the speed. Okay. Well, this is a typical equivalent circuit, but we didn't put a load on this one yet, okay? We haven't put a load on this one yet. But this is just a computation of mutual inductance versus self-inductance. So for this one, depending on the turns, how many turns of the windings you put on the armature, okay, or in the field. So these are that. So inductance times current will give you flux, okay, flux. So usually we denote the mutual inductance times excitation current. That's basically phi f. We call that is kV. Okay, when you buy a DC motor, okay, or even brushless DC motor, so usually we'll ask, oh, what is the kV value? kV value. So that kV value is or DC machine constant kV. So it's a very important parameter. The higher is more expensive kV value. So with that, we know the electromagnetic torque is actually proportional to my armature current, IA, and this kV, okay, kV. And this kV is usually constant because field winding, we don't change it, okay, a fixed power supply. So with that, so this is a winding, this is my armature, and the link to my load, okay? So then this has to satisfy Newton's second law, meaning this is load torque from load. This is my providing torque to you, and this is my electromagnetic torque. This is my J is a Newton's second law, right? Moment of inertia times angular acceleration. And this, of course, is damping, okay? Viscous damping. Viscous damping, okay? That this Bm is a viscous damping coefficient proportional to my speed. The bigger the speed, I have a bigger and resistive, okay? A frictional torque, okay? It's friction torque. So then this is the balance, okay? Or in other words, I fix this one in this side, then move everything on this side, okay? So this comes to this picture. I'm teaching you right now, okay? So now we have a load, okay? We have a load, TL, okay? We have TL. So this is amateur, this is a field circuit. Sometimes it's also called field excitation. Field excitation circuit. So you provide a VF, then you have RF and RF, okay? So then how fast this one will move depending on the I, okay? So we know that answer. So all these coefficients in here, so this is called electromechanic part, the motor part. This is called a load part. So you have two parts, okay? So you have a electromagnetic torque, TM, from M stands for motor. And then you have damping, viscous damping coefficient B. You have a load, okay? This is a shaft to connect to a load, okay? And usually electromagnetic torque, and this thing is the same symbol. This is we know Bm, okay? We know omega m is a motor, is omega r. Ra is the same, okay? So all this, okay, physical. So this is physics, okay? This is physics. You should not break this physics, okay? Okay. So that is our physical models. So we have a name for it. So what is the name for RF? This is the field excitation circuit resistance. This is the field excitation inductance. This is armature inductance. This is armature and resistance. Okay, this is a rotational speed. This is a damping coefficient. This is the electromagnetic torque. This is a moment of inertia of the load, of the motor, I'm sorry, of the motor. Okay, the rotor. So I said we have 4 types of excitation method. Different methods will have different characteristics, okay? So let's take a look at this one. This is widely seen. It's called separate windings. So you can provide VA, you can provide VF. So you can change VA, change VF, then you change the speed, okay? So this is separate excitation. But you can see this might be expensive. Or what if I do, what if do the shunt connected DC motors, okay? So you can see this, the same VA will do this excitation. Then also parallel, we provide that. This is called equivalent circuit for the shunt connected DC motors. So the characteristic is different, okay? Finally, you can see the torque is proportional to the omega by such a way. If you draw a plot, you'll see that your torque versus omega, okay? So when omega is 0, the torque is big. When omega is high, the torque is small. Okay, so we have this characteristic for the shunt connection. But for this connection, the first separate winding excitation, the torque is actually not like that. Okay. So most of the small handheld fractional horsepower DC motors have this separate excitation. So you just control the amplitude of the applied armature voltage. Okay? You don't do the field excitation at all. This is also inconsistent to the permanent magnet DC motors. Okay, so this is shunt connected, separate connected, and shunt connected. And the shunt connected, be careful this torque and the speed relationship. Okay, we already said that. And steady state operation for the shunt connected DC motor. There's a omega, when omega is 0, you have a steady state armature current. So that current is linked to the armature resistance. So, okay, the armature resistance, it could be large. So when you start the armature, the current is big, then you got stuck for too long, you can burn your motor, okay, basically, okay, can burn your motor. So sometimes we purpose to add some resistors, add some larger resistors to get it to start up. So your current is small. So that part need to be careful, okay? So they're also series connected DC. So this is a voltage provided, then you go through this field, then go to this armature. So it's called series connected DC motors. Again, they have a different characteristics as well. The physical difference in the field winding of a shunt machine versus series machine is, let's go through that. Shunt connected field winding is a large number of turns of small diameter wires are used, making the resistance of the field windings large. The reason is when it is large, then the startup current is so slow. It's smaller. Series connected field winding in series with armature, designed so as to minimize the voltage drop across state. Okay, the winding is wound with a smaller number of turns and with lower resistance wire. So you don't have a lot of voltage drop up due to the field excitation. So let me see. Yeah, they have store torque means when omega is 0. Okay, well, omega is 0. What is the torque? Need to sustain that. Okay. Well, I think the store torque is high. Therefore, it's used for high startup torque situation. They're also compound connected. So you have series and parallel. Part of is during the, can we cover the basic of what happened during the final? Can we cover the basics of what will happen during? That is next week's lecture. I'll do that, okay? I'll tell you what's in the exam, don't worry. But we really need to know some of the basic connections. DC motor. So we haven't seen the transfer function yet. So we know we have a RA and IF, field current and armature current. They are connected with this D. By the way, D is ddt, okay? and TE is kV times armature current. Okay, and this is Newton's second law. Okay, and this is just a KVL and yeah, KVL. So in the end, you are seeing something like this. So basically, you have a U of F, it's a voltage going through like this, then you get a current. Okay, and the current going through this one, you got flux. Okay, the flux times IA, armature current, you get a torque. Torque, and this is load torque. Then add to this one, you have this term. Then you get omega. The omega times what? So the omega is here. This is omega. This is the RAF. This one. So this one. They will give you what? Back EMF. Back EMF. This is VA. You add this one. So then you go through. This is like a first order circuit. You have a armature. You have a inductor. So this P is like S. You can say P is S, like X Laplace transform. Okay. So this picture versus this picture, I see they are the same. Okay. These are all physics motivated model. But if we check the overall transfer function, we're going to see something like this. So you have VA, you add VA in here, you get omega in here. But this is a KV feedback. You have TL in here. So that's the final block diagram. And because you are using permanent magnet, so you don't have to, you only provide the KV, you don't have to get the EF, okay? You don't have that. So this is a nice thing. So so if we say that I give you a voltage, then go through a box, you give me omega. So usually we put it here, K versus TS. So this first order system. This is really very crude approximation. On the other hand, it's also understandable. The reason is the time constant in here, tau A, okay, is much less than this J. Okay, this J here. It can be ignored. In other words, excitation dynamics is much faster. You get the transient will die out very quickly. Okay, so therefore it can be ignored. Okay. So we can stop here. Summary, we haven't talked about motor selection. We'll find time to do next time. So next lecture, we are going to try to explain to you the brushless DC motors as much as we could. We can stop here, sorry. I know you are very urgently want to know what's in the final exam. I think it should be relatively easy. I will make it easy at least because of this distant learning. So you should go back to your homework, midterm, quiz, okay? I'll make sure 70% of the questions are from them, okay? Will it be open notes? No, not open notes. Then you just go to your homework, you can do. Just do it, okay? Use your pen and paper or electronic pen, electronic paper. So, yeah, this closed book, please. Yeah. Okay, so I'll pick up questions from homework, quiz, and midterm. I'll give you the final exam of last year. I'll walk you through what was there and why I put there, okay? Why, so some of them are basic expectations and why what you should learn. I'm sorry, I'm 5 minutes over time. So we'll talk more on this one next Monday. How about that? Okay. Bye-bye. Take care.